I think I'm live there. See what's happening over here. I'm sure something's broken because it always is. And for Twitch, we started a little bit late. People are very passionate about science. It is broken. That is why we check. I don't know why that gets reset.
You change your output solution.
I think it has to do with whether I start up like OBS or this thing first. That looks reasonable. That looks reasonable to me. OBS is like both great software and terrifying software. All right, cool. I still don't know what day it is. It's all kind of a blur. We're talking about the heap here at ASU in CSE466. Let's talk about the heap. So memes, it's only been a couple days, but there were a couple memes and they were at least on brand. So we talked about GDB. Hopefully at this point you realize GDB is kind of the answer to all your questions. If you aren't using GDB, it's very hard to answer those questions. But one of the trappings of GDB is there are challenges that randomize values based upon the flag seed. I don't know if they're in this module, are they?
Yeah.
All right, that makes sense why this meme is here then. And if you use GDB, and you are not in practice mode, you will end up getting this weird error. Says flag seed, sig abort. Has anyone figured out why that's happening?
Because the flag permissions are dropped when you get GDB.
Okay. So the statement was it's something to do with permissions in GDB. Does GDB drop permission? And the answer is yes, GDB does. The flag permissions are the same. The thing that drops, if I fire up, does anyone know we're not in ROP anymore? We are over here. Anyone know a particular challenge that does this? Probably this one.
Yeah.
So you'll notice I'm always starting things in privileged mode because I've shot myself in the foot doing this that many times. Dojo.college. Secret numbers. And so if I run this thing, it works. If I GDB this thing, it does not work. And we end up in, as that meme said, we can look at the call stack here. We are raising a sig abort. It is somewhere in some function called flag seed. I don't have to understand all of this, but just like try and make sense of the back trace. Where the heck am I? Like, an exception was raised in this flag seed function, and that bubbled up into this. This flag seed function is happening in kind of a weird spot. And I think this is honestly kind of a, yeah.
Look, the string is like cut off, like it's offset. Like you need to drag the
Your video is
screen
different
up
aspect ratio.
on that.
RSP. All right, looks good.
Show you on my phone if you need to tell.
Oh, at the bottom?
Yeah, at the bottom, you need to like drag the view up on OBS. It's like cut off at the
All
bottom.
right, we're gonna distort our. We're just gonna be.
You can't see the pitch.
Oh.
It's like cut off.
Thank you for that.
That looks
Thank you very much.
Yep.
And so when we get GDB exploding here, a good way to kind of know what's going on is to look at the call stack of the backtrace. This is where that exception was raised. And if we look at the functions that like called that got us there, we see flag seed and we see libc underscore CSU underscore event. Now this is kind of like this weird magic spot, which I think is kind of a failing or trapping of the challenge, because this is happening before main, right? Like we don't see main in here. This is actually a startup thing that is happening before main is called as part of launching the C runtime. You don't need to know this, but that's what it is and why the call stack is where it is. There's a way you might have done this in 365. Do you remember when we had program misuse and we had I think SSHD or SSH keygen. SSH keygen was a program that you had to exploit, and it made no sense. You're like reading these man pages. You're like, it doesn't take a file. I don't know what's going on. One of the elements of how to take advantage of that was to use something that was called a constructor. You had to do an attribute constructor on a function on when a library was loaded. I know I'm spoiling something, but what the heck is an attribute constructor, right? But it's at load time when this thing happens. As part of booting up the C runtime, you can say before main is even called, do some work. And that is where this flag seed in the actual implementation of the challenge is calling flag seed. Again, you don't need to know this, but I think it's an amusing thing to point out as long as we're here. So then I would want to probably look at the disassembly of this. If I'm just using GDB, there's a whole bunch of nonsense. That's fine. What do we see this thing does? When we're reading assembly, what we really want to look for, again, this is just like a reverse engineering, looking at assembly practice. You want to look for like call functions and just feel, all right, what's happening? What are we calling? Okay, we're calling open, we're calling read, if we open, then if open fails, then we're going to assert this failure, which is probably where that assert is coming from. How do I know what file is being opened? It's not a trick. It's the first argument of open, the path that we're going to open. And if we look right here, GDB will tell me this is the address that's being loaded into that register. If I were to examine the string right there, it's trying to open flag. It is opening the flag and then reading it. Where's the call to read? My goofy? There's a call to read in this thing, right? Yeah, okay, there's the call to read. So we're going to read the flag into memory, and then we're going to call sran. Did anyone by chance, because this came up on the Discord, look at what sran does?
It seeds for the random function.
Right. sran lets you set a seed for random values, right? There's a couple ways you can generate or get random values on a Linux system. You've probably seen a couple at this point. One way is you can access dev random or dev srandom. That is a way that the kernel exposes as a device. If we take a look at dev, we can take like the head of dev random. There's some random bytes. I can do the same thing with, oh, it's not srandom, it's urandom. I apologize. At this point, these both do the same thing. Historically, they used to be slightly different. And so they exist as two different paths for backwards compatibility reasons. And that will give you random bytes. Another way, if you want to have a repeatable pseudo-random system, is you can call rand or srand. srand allows us to set a seed. And so what this allows us to do is generate a random value, but make this random value consistent for you because we are seeding it off of the flag, which is something you don't know. The reason it fails, as was pointed out, is because GDB drops permissions. Is there a way that I can get GDB on this and make it work?
Attach.
Okay, somebody says attach.
Just like wait for it to do its thing.
What is this thing, baby? No, we renamed it. They now have cool names. If you can type, then you say I want a GDB attach 611. I'm not allowed to do that. Right? Operation not permitted. The big nugget here is I can attach, but I have to be root, which means I have to start it in practice mode. You have to be root to attach to another running process. But the trick here was not specifically that I needed to attach, but I could also sudo GDB and then run the challenge. And now that GDB is running as root, the challenge is still running as root as well. So I didn't have to attach, I just have to make sure that while I'm debugging it, I'm running as root. But what is part of the pain here? Can I just GDB grab the secret and that's going to be the secret in the other version? Why?
It's seeded to pwn.college in practice.
Right. It's seeded based upon the flag, and the flag in practice mode is pwn.college practice. So we can't abuse GDB to get the secret value. Cool. So a couple good memes there. I said you're going to hear this every day until we have the exam. Today is no exception. The exams are 1021 and 1023. By this Friday, which is tomorrow, you will get a topic review sheet. I tentatively have that. Michael and I ran through what that looks like. I'm still just going to sit on it for another day because that's what I promised you. We will cover all topics through this module. Anything that's in program exploitation will not be something we talk about on the exam. I plan on having one day of class be Q&A. So you get the review sheet, you go look at it, you write down and look up whatever you want, and then you can ask about anything that's on this review sheet if you want. If you don't, great. But the thing that I don't want to be an excuse is, hey, we didn't talk about this, I didn't know what this was, etc. It's not meant to be a hard exam. I don't want it to be a hard exam, but I do need you to put in the effort to look up the things that I tell you you need to know. Yes?
What's the format for the exam?
The format of the exam. So the format of the exam is going to be somewhere between, don't quote me on this, like 7 to 10 questions. They're going to be open-ended. Like free response, I guess it's not multiple choice, it's not true false, it's not fill in the blank. It is a question. An example, the question is going to be, I'm expecting a response of like 3 to 5 sentences, or the question is going to be something where I say like, draw a diagram of this. The type of concepts or things I'm going to be looking at to give you a preview of what is on this review sheet is what is the PLT GOT? What is railroad, right? Why would you want, why does ROP work in some scenarios where like shell coding does, what's the difference between these things, right? I just want you to have like a basic demonstration of these concepts or techniques, right? What is NX? Are these hard questions, right? What is NX and how does it impact an exploitation? Some reasoning about memory, some understanding about space, right? If I'm like looking at a binary, distances, these are all things that you hopefully have applied done, right? It's meant to be an easy exam. It's supposed to ask questions about things that you've already done, but I'm also going to provide you a list of things. So that way, if you're just like, oh, well, there was this GOT thing and there was this video and I did it, but I don't actually understand the PLT and GOT and how this works. Cool. Let's talk about it for a day. Because I don't want it to be a surprise for you guys. And the nice thing is you do get the handwritten front and back. So anything I say, you can just write down and be like, all right, cool. I got it, right? It's meant to be easy. Put in the effort. You'll do fine. So anything through this module is fair game. You do get one handwritten sheet, front and back. You can write on both sides. I don't think you'll need it, but if you want to be over prepared, you certainly can. All right. I'm trying to be as forthcoming as I can as far as what we're going for there. Basically, if you didn't just LLM your brain through it, you should do fine on the exam. Demo plans. Is there anything that you all are particularly stuck on? Did that answer your question?
Yeah.
All right, cool. Was there anything that you were particularly stuck on? If not, I'm going to try and more coherently say what I did. Okay, Twitch is happening. Give me a sec, Twitch. I'm going to try and more coherently say what I rambled about on Tuesday, and then I am going to jump into kind of a different way of exploiting the game, unless you have something you want me particularly to talk about. All right, the class says nothing. Let me see. We just have hype, huge, big. Is there a slideshow? Yeah, I don't do slides. That's right. Thank you, Twitch. Coolidge. It's all this white guy's fault. All right. Whatever. Internet meme fight. You guys need to make more cool memes because now I'm pulling from memes from last year. All right, in order to pad my slides. One of the things we saw on Tuesday was that the Tcache isn't that bright, right? It blindly trusts metadata. And one of the things that I did was I showed that if you corrupt that metadata, you can get the Tcache to think I have multiple chunks that I'm going to return, but it's all the same data that's pointing to itself. Right? We didn't get to see that. This is a fun thing you're all going to run into in the next week, and we don't talk about it until Thursday because there's no class this coming Tuesday, I believe. We have fall break. But the last, I don't know, 4 or 8 challenges from like 16 onward play with this concept called safe linking. It is a fine pre-recorded video where you get to see my smiling face instead of Jan's. Safe linking tends to be students' least favorite thing. In the heat for sure. You're going to get stuck. It's going to be fine. We'll talk about it on Thursday. Next week, Thursday. All right. More stuff. You guys are just a whole bunch of trolls. All right. I don't know which one of you are having a jolly good time there in Twitch chat. Okay, so I had this heap demo, if you'll recall. It was just this toy program where we can malloc, we can free, we can safely free. What was the difference between freeing and safely freeing?
Clear the pointer. Safely free.
All right, if I in my program here, when I say safely free, after I call free on a pointer, I'm going to null it out. Where is this pointer located in memory?
Anywhere.
It really could be anywhere. That was a lame question on my part. You would think the stack or the BSS from memory, this one happens to be in the BSS, but it is not like explicitly location of the pointer does not have to be the heap is what I'm trying to get at there, right? It is the location where, do I have a do.py here? I do not. User bin m python 3 from pwn import star p equals process a dot out. Okay. Now I showed a couple patterns on Tuesday as far as patterns that allow us to access metadata and corrupt this thing. Does anyone remember any of them? Or was it all just an incoherent mess? It's fine if it was an incoherent mess. By the way, I just need to know. Incoherent?
Use after free.
Okay, use after free is a thing. What is use after free? And how do I pull that off and generate a use after free vulnerability over here? What is the access pattern? Malloc freeze, reads, writes. What am I doing?
Malloc free.
Okay, malloc. Let's see what this thing wants. It wants a size. Doesn't matter how big I make it.
It just has to be the same size as the free.
Okay, 20. I malloc something of size 20. Then you say I'm going to free it. Can I safely unfree it?
No.
Okay, so I do need to unsafely free it.
Assembly. For the free.
I'm sorry?
That should be assembly.
Thank you. Okay, so do I have a use after free right here?
We're not using.
I'm not using it for anything, but do I have one?
Potential.
Yeah. All right. Why is the use after free valuable to me? Why do I care? It's cool science word, like
Because the heap guy thinks that it's his. You can still touch it.
okay, the heap guy thinks it's his, but we can access it.
Yeah.
All right. Do a little bit of paraphrasing there. So when we malloc it, we're saying our program wants a region of memory that's 20 bytes in size. When we free it, we're telling the heap we're done with that memory, but we still have a pointer to that region of memory. What is one thing that I can do now that I have this use after free? Why is this a valuable vulnerability or primitive to be aware of from an attacker's perspective? Okay, so I could print it and I could get a pointer. All right. I have write bytes from pointer. So let's see what that thing does. And we're interested in slot 0. I'm going to say offset 0. And I want 8 bytes. I get some, in this case, I get, that's interesting. That doesn't seem right at all. I agree. This program is cursed. Because, or is it? What should be there?
The next.
Okay, the next pointer. Why is there no next pointer there?
Oh,
No next allocation.
Yeah, there's no next allocation to point to. So the next pointer is null, right? We did print the next pointer. It just didn't provide us any useful information. How can we fix that?
2 mallocs, 2 free.
All right, 2 mallocs, 2 frees. Can I do malloc free? Why?
It'll use the same chunk.
It'll just give me the same chunk back and forth. I like it. Okay, so we're going to update this a little bit more. Hopefully, I can write Python code today. I cannot write Python code today. 6. Whatever. We'll go like this. Boom. Now I want 6 because I want to write from pointer. I'm interested in which pointer. So since I have 2 use after frees now, right? I have a use after free of slot 0, and I have a use after free of slot 1. Which one should I be interested in, and why?
Someone.
Okay, somebody says slot 1. Why do you say slot 1?
Because that's going to be. That's the head of it.
So that is the allocation that is at the head of the list. I agree. We're going to draw this amazing linked list thing here in a second. So let's see here. I gave it 6. Oops. Okay. 6. And then it wants a slot. You said 1. I want an offset of 0, and I want 8 bytes. Did I do that right? I did. And now we see I get some bytes over here. And my claim is this is our next pointer. We can get that for sure by calling this. Did I? It's not big enough. These were the bytes that I printed. C006912D. That does match up with this. I'm just printing it. If I print it as a string, we read it this way. We display it as a decimal number. It's going that way, right? But we are printing out that next pointer for that chunk. So that's one reason why a use after free vulnerability is useful. I can get a pointer. I can print it out. What else can I do? If there's a use after free vulnerability.
You get the key.
Okay. There's this other value. Somebody points out. It's called the key. What is the purpose of the key?
Make sure that it doesn't double free.
To make sure that it doesn't double free. That is an accurate statement. So the way, if I were to try and free, what is the slot 1? Again, we'll get an error message that says error double free detected. The way that the heap knows that this allocation has already been freed is because this is a magic constant value that it is checking for. That's how it knows that it's a free allocation. Why does the heap feel okay putting this value, this key right here?
Because you freed it already.
Because I freed it already. And the contract is after I free it, the heap can use that memory however it wants. And so the use after free is, well, I told the heap, I'm done with this. And the heap's like, cool, I'm going to write this value here. I'm going to use it to make sure you don't free again. I got you, right? But we have a double free, and the program allows us to still access this memory. So what do I want to do if I want to do a double free? How do I take advantage of this right now with this use after free? I want to free slot 1 one more time.
Change the key.
Change the key. How do I do that?
Right, arbitrary data.
Write arbitrary data. So we will hit 5 to read from pointer. I'm going to put it in slot 1. I don't know what the next question is. We're going to guess the answer is 0. Okay, you didn't like that.
Bytes.
That's okay. We're going to go 5, 1. I want to write how many bytes?
16.
Literally any.
Literally any.
As
So
long as it's not 0. Because
how about 2? Okay, 2. All right, reading from standard in. Now, your claim is I corrupted the key.
he's wrong.
That's okay. It's okay to be wrong, right? As long as we can experimentally prove that we are wrong, right? The pointer points to the allocation, which starts at the next pointer, right? So here's our AA, and we managed to corrupt the start of that next pointer. We didn't make it to the key. What is the distance to the key?
8 bytes.
8 bytes. So in order to corrupt the key value, I need to write at least 9 bytes. All right, we will read bytes to the pointer. I want to put it in slot 1. We'll read 9 bytes. We'll give it a bunch of A's. I need to be careful about this or it may just yell at me. 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. Let's cheat and take a look at this allocation. What I've managed to do now is I have overwritten with the heap things at the next pointer with a bunch of A's. And I have overwritten that least significant byte of the key. So now, if I try and free slot 1 again, it happily did it. We didn't blow up. We didn't get any crazy here. All right. So that was how we can mess around with a use after free and start thinking about corrupting the metadata that is on the heap. Yeah. Now, that's cool and all, but it's a little bit hard to visualize. So hopefully the technology works today. I want to draw this thing. And let's see. So we have, boop, that's text. Believe in the technology. That is not a writing tool. All right. So we have something that you may or may not be able to see because of the technology. I want to be a believer.
Might be over.
It could be. It could be all over. All right. When in doubt, restart the technology, right? Turn it off, turn it on again. We hit this, we hit this. We believe. We believe really hard. This is like mission critical. We were depending on the drawing. All right. We're going to have to take evasive maneuvers. All right. Okay, wait, you're zoomed in over here. Maybe we do have power of the technology. You see this?
You're using the wrong tool.
Using the wrong tool. See, this is what happens, man.
Okay.
All right. The technology works. All right. I can explain a T-cache I can't draw on a Apple application. All right. So we have some region of memory here, which we refer to as the T-cache per thread struct. What is the purpose of the T-cache per thread struct? What is stored up in this thing? Like if I were to say, tell me what data is in this T-cache per thread struct, what would you tell me? Okay, there's something about bins, there's something about counts, and that's really the right answer, right? We have this, it's really not that crazy. There's 2 arrays inside the T-cache per thread struct. The first one is an array of ints, which we refer to as size. The second one is an array of pointers, which we call the head pointers, right? Every pair of size and pointer we refer to as a bin. Why do we call this a bin?
It's like how big of the malloc.
Yes, the bin is related. I shouldn't say size. I should say it is called size in the code. Screw it. So we'll. It's called a bin because it is we can think of it like a bucket or a collection of treed allocations. Now, what did we do over here? So this bin, for example, could be chunks of size 0 to, we'll say, hex 20. I don't know. I'm making this up. This could be hex 20 to hex 40. There is some rhyme or reason. You don't have to know them. But there are specific sections or specific bins for chunks of specific sizes. All right. Over here, what did we do in our code? If I were to visualize this thing, I malloc. All right. So when I malloc, what happened? Does that change anything in this drawing that I have here so far? No. Well, where did malloc get this memory from? It's giving me a pointer. Yeah. Okay, it's in the heap. Is the heap part of the T cache? No, the heap is just a region of memory that's chilling, right? If I were to attach GDB to this and run VM map, we'd see it's just a region of memory, much like the stack is, right? Much like the read-write data region is, anything like that. And so we have somewhere here just heap memory. Okay? Now my code called malloc. Where in my picture does malloc get the memory from? Where is this pointer? Somewhere in the heap, right? We can, for the record, the heap, at least for this, our purposes here, is deterministic. So it's not 100% true, but we can reason that this is chunk 1. And what malloc returns is a pointer to chunk 1. Then I malloc again. Cool. What does that malloc give me? Cool, it gives me some other chunk. Who cares? It's going to be right next to it. This is chunk 2. I get a pointer to that thing. Now we notice that in my drawing here, these are right next to each other in the heap memory. That's because I'm assuming that the heap hasn't done any allocations or frees already. We're assuming that we just kind of have a naked heap that hasn't been out malloced from. All right, then I free 0, then I free 1. Does this update my picture at all?
Yes.
Cool. How does my picture get updated?
It's added to the T cache.
Okay, what does it mean? The answer, the statement was it gets added to T cache, and that's correct. What does that mean as far as my drawing goes?
Depending on the size of the malloc, the size of the corresponding T cache array index gets updated, and the head pointer gets added.
Okay, so I only like halfway heard this. I'm going to try. Based upon the size of the chunk, and I don't really care about the bins. We'll say everything is in bin 2, all right, for all I care, right? This is the chosen bin. How do I update this when free is called? We free, what did I free over here? Chunk 0. Okay. Which I guess we're going to call chunk 1 because I can't have consistent numbering. Why would I? So what gets updated? It gets pushed to the head of the list. What does that mean? This is my list. My size is currently nothing. My head pointer is currently nothing. How do I push this to the head of my linked list? Head pointer is going to point to chunk 1. Bam. So now I have this scenario. What else changes?
Size goes from.
My size goes to 1. Beautiful. All right. Next thing I do is I'm freeing chunk 2. How do I update my drawing to do that? Nothing's gotten messy. Thought it was a bad drawing before.
The head pointer will point to new chunks of chunk 2.
Okay. So now my head pointer points to chunk 2. All right.
And then the next metadata in chunk 2 is going to point to chunk 1.
Uh-oh. And then chunk 2 is no longer my chunk, right? It now has a couple things. I'm going to make chunk 2 a little bit bigger here so we can do some scribbling. Chunk 2 is suddenly larger. Enlarged for your enjoyment. That's what they do on like cereal boxes, right? They enlarge the size of the flakes so you can see the texture. Yeah. If you ever read the fine print in like the bottom right of a cereal box or a lot of commercial products.
Large for like
Yeah, enlarge for details so that you can appreciate the product. So we write a next pointer, right? What else do we do? What? we're thinking hard. No, but like this is good, right? There's something else. There's a reason that I made chunk 2 bigger, right? Yeah, there's a key. All right, I'm down. Right, we get this key. What?
one had a key.
Yeah, one technically had a key. It's chilling over here. Whatever. Well, where does this next pointer point to in chunk 2? It points to 1. So the next pointer does one of these. And so now I have something that looks like this. right? This is what's actually happening in memory, but I think this is kind of a mess to look at it. Right? Do you agree or you don't like
Right,
that?
also size gets,
Oh, you're saying there's something about size. What do you want?
it's gonna be 2 now. It's not gonna be 1.
Oh, yeah, my size does become 2. All right. So this is what's actually happening in memory. But when we start, and the reason that we have a use after free is these pointers that Malik returned were not clear, right? And so the userland program. Did you have a question?
So the next pointer will point back to same child.
As you can tell, I'm a professional artist. I'm glad that you noticed. This green guy, I'm claiming, is chunk 2. And then we'll add some more color. Blue's a good color, right? This blue one here is chunk 1. All right. What I'm saying here is the order of operations matters when we think about what's getting freed. And we have to think about what happens when we append to a singly linked list. The order of freeze is what determines the order of this linked list, assuming that we're all interacting with the same bin, which we are in this case because every chunk's the same size. So I'm freeing, I'm numbered them 0 indexed here instead, so whatever. Roll with it. I'm freeing the first allocation, then I'm freeing the second allocation. And what that means is when at my time when I'm doing this free, my head pointer points to the first chunk because that's the only thing that's free. But when I do this second free right here, I'm appending to the linked list, right? We need to grow it from a size 1 to a size 2. And the way we do that with a singly linked list data structure is we append to that, we update the head, and then we write the next pointer to be the old head. That is the operation of the linked list. But we see when I try and draw this and think about how things really exist in memory, this turns into a giant cluster, right? I kind of knew that was going to happen. Instead, if we can just accept the fact that these chunks live in heap memory, we can organize this a little bit cleaner to visualize this. Instead, what I would say, if I can choose the correct drawing utensil, is my next pointer is pointing to chunk 2. It is pointing to chunk 1. And I would just think about it like this. If I malloc something, which chunk from this bin, what chunk am I going to get? Chunk 2. And if I malloc 2, what's the chunk that I'm going to get? Chunk 1, right? Now, this is something that we've managed to do just with this use after free, right? Now, the last thing that I showed on Tuesday was that we can abuse this chain to get a pointer to an arbitrary location. How did we do that? We kind of already did it. When I tried to corrupt that key, what did I also do?
Overwrite.
I overwrote the next pointer. But the next pointer is what determines what this linked list looks like. You agree? So, do I have the ability to corrupt this pointer from 2 to 1? Yes. Let's do that. Let's point it somewhere. Where do we want to point it? There is no flag. This is I agree it'd be cool if there was. Unfortunately, I didn't think that far ahead when I wrote this demo. So we'll GDB A1110. You said Etsy something, Etsy password?
Yeah.
Unfortunately, that's also not mapped into this binary. So somewhere that we may want to point it to, what is our like high level reasoning? There's some places where it makes sense to point, and there's some places it doesn't make sense to point. Does it make sense to point it into the executable section of the binary? Somebody says probably. In this case, maybe, but we'll inevitably have problems. the executable section of the binary, it's not the fact that it's executable, but the fact that it is read-only can be a problem. Because what does the heap do when it is constructing these chains? It has to write the next pointer. It has to write the key. Or when I malloc, does the heap do anything with the key that was there? It nulls it out. It's like, no, man, the key was for me, not for you. So before I give you this allocation, I'm going to zero it out. And so if I were to point this next pointer to somewhere that's read-only, is the heap going to be able to do those things? No. And so when it tries to do those things, what's going to happen?
Crash.
I'm going to crash. Anyone want to go more specifically with how I'm going to crash? Check full. That's all good. It's all good. So where is somewhere that we may want to point it to? Somewhere that is read write. So we could go here, we could go here, we could go here. There's lots of places, but the high level goal is let's point it somewhere that is read write. And so I could overwrite that next pointer to be somewhere in read write. What does that do to my drawing here? My linked list.
Second arrow.
The second arrow, it's gonna be red, right? It's the evil arrow now. Give me a red. Oh, we don't have the technology. All right, do we? Yes, the red evil arrow. All right. And the red evil arrow points to our secret value, or we'll call it could be the flag, right? Oh, that makes my handwriting look so much better than it is. Thank you, Apple. And so we can do this. Now, once I have overridden that next pointer, how do I get the heap to return me the secret guy? I've used the use after 3. I've overridden this next pointer. It's not a trick question. I malloc once. Malloc once is going to give me what? Chunk 2.
Malloc again.
And I malloc again.
Gives you secret.
And it's going to give me secret. It's going to give me a pointer to secret. All right, so that was cool. And that is what I tried to talk about on Tuesday while like frantically being like, oh my gosh. Any questions about this? No? Good? All right. So the second thing is just a different way of kind of thinking about the heap. The first way of thinking about it is the metadata and thinking about it in this linked list. The other element that is important is this up here where we say, well, these chunks are also located right next to each other in memory, right? And we can utilize this in an exploit as well. So we have some giant heap area. Set that free. What I'm interested in, hopefully this thing prints it out. It's not free. Let's do this. Let's just malloc twice. It does not print things, because why would it? We'll print 1 and we'll print, or print 0, print 1. What I care about is the pointers that are returned. So I have one chunk. Chunk address, it's a little bit higher. I have one chunk address right here that is at, I'm gonna have to write this down. We'll ignore the higher order. I'm just gonna grab, we'll say 86C0. 86C0. You see I'm grabbing that from this right here. This was the first chunk that I malloced. The second chunk that I malloced is where? OX86E0. How far apart are these? Hex CD to hex 20. Okay. So I have one chunk that's here, and then I have another chunk that's right here. Now, I could keep this giant box, but the giant box doesn't help us here if we just understand this is all contiguous memory. So how do we make things big? Bam. We almost understand the technology. To kind of, at this point, it's kind of a meme from back in program security. What is something that we know about memory locations that are right next to each other? Like we messed around with this on the heap, right? Or on the stack. 086C0. Do I have the ability to like grab and move things? That would have been. There's a sweet lasso? Ted Lasso? No, no Ted Lasso. So if I write to my first allocation, where does it start writing? So it's writing here, right? This is the location that I was given. And behind that is a little size value. It's going to be OX2. That's actually going to be, I think, 20. If this is hex 20 in size, what happens if I write more than hex 20 bytes? I'd start clobbering the next chunk in memory, right? And so I could, for instance, A, and we could overflow from one chunk into the next. All right, that makes sense. But we could be a little bit more clever. What happens if I 3 my second chunk here? Right now I just mallet 2 things. So I just have 2 of these. I've got a pointer to both. Well, when I free it, it's free the send line 2, 1. This is freeing slot 1. What is we said the heap's going to write this metadata in this second chunk as a part of freeing, right? What does that metadata look like?
Next.
There's a size, there's a next, and there's a key. All right. Now, as part of freeing this, it gets placed in my little Tcache guy. We get pointed to it. How does the heap know how big this thing is?
The bins.
Okay, so right now it's in the Tcache, and so while it is in the Tcache, the size is determined by which bin it's pointing to, right? And so if I were to malloc something of size hex 20, I would get back this pointer. So there's not anything fun for me to corrupt at this point. What if I don't free it? And when I don't free it, there's no next pointer. And there's no key, right? I'm free to use this memory. Is there still a size? You say no?
Oh,
Size metadata is still there. The size metadata is behind my pointer, right? The user writable memory is this stuff right here. This is where the user is allowed to happily use this thing. And in this trunk, the user is allowed to happily write this stuff right here. What happens if I go, I don't know, 8 bytes past this? I start corrupting the size value of that allocation. So what if instead of reading in 20 bytes in the little happy region, I instead read in 28 and I start overwriting this size? Could I make it, I don't know, hex 80? Could I do that? Sure. Why not? What happens then when I free this pointer? What bin is it going to go to? Yes. So I have a chunk that was allocated as size 20. And I'm behind it. I go and I corrupt the size value. I probably want to make it hex 81. Why would I want to make it hex 81? What's the difference between hex 81 and hex 80?
bytes.
No.
I don't know
I
byte.
think the previous use well,
Yes. The least significant nibble of the size contains a number of flags. The 1 bit is whether or not the previous chunk is in use. For our purposes here, this 1 being set informs the heap that this chunk is in use, which is what we want the heap to think. So then when I free it, it goes to a different bin, right? Then when I malloc something of size hex 80, would I get back this address? I would. But how big was this trunk? 20. Now in my drawing right now, this seems like, who cares, right? There's nothing important over here. What happens if I add in chunk number 3? 3 chunks. This is I'll call him my victim chunk.
back in
All right, the victim chunk is going to have a bad day. The victim chunk is also going to be of size hex 20. So I need to pay attention. If I pay attention to the location in memory of these chunks, I can go from chunk 1 to corrupt the size of chunk 2. Then zoom out a little bit. We'll free chunk 2. It's going, and we're going to go with everything's malloc size hex 20. I'm overriding this with size hex 80. When I free this chunk, it's going to go to the bin for size 80. Right? Chunk 2 goes to bin for hex 80. And I malloc again. So this time I'm going to malloc something that's going to retrieve that hex 80 size. What does the end result of this thing look like if I were to try and draw this? I still have my chunk 1. Chunk 2 is how big now? Does the heap think? Hex 80 bytes. So chunk 2 is really big. Right? Chunk 2 is a monster. It's a chonker. Chonking chunk 2. All right. Your size. Oh, you got to tell me that I'm failing to display. Yeah, thank you. All right, you got. Come on. Okay. Chunk 2 is of size hex 80. Where does chunk 3 fit in this drawing?
It's inside of 2.
Chunk 3 is somehow inside of chunk 2 now. Right? That's why chunk 2 is a chunker. Because now we have chunk 3 right here of size hex 20. What we've done here is we have leveraged the fact that these chunks are located next to each other. See, I moved the picture on the iPad, and then it doesn't make the picture move on the laptop. We've leveraged the fact that these chunks are located right next to each other in virtual memory. It is slightly a buffer overflow, right? Which is why it's kind of a meme. But we are writing from one chunk to corrupt the size of the next chunk in memory. Then when we free it, it goes into an incorrect bin. We malloc it, and it comes back as a bigger bin. And we end up with this scenario where we have chunks inside of chunks. This is called an overlapping allocation. Yes?
Can I then get values from chunk 3? Like if I
Can I get values from chunk 3?
using chunk 2?
So what I'm drawing here is what's happening inside the heap and how we think about the chunks. Whether or not you can read chunk 3 from chunk 2 is going to depend upon the application, right? And how it's using these pointers. I will say that I believe for this module, for the challenges at least, the menu that we provide you is like malloc, free, write, read, and we may place a limitation, but that limitation is all at most, or I'm sorry, at least going to be the size of the intended allocation, right? We won't let you malloc 80 and then only write 8 bytes. If we let you malloc 80, then you're allowed to write to the 80 bytes or hex 80 bytes because that's the contract of how you are asking the heap to use, right? That's not you, is it? Twitch? Okay. So if I malloc hex 80 bytes,
Is that really the
okay, yeah. So if I malloc hex 80 bytes, the contract with the heap is that normal user read writes should cover everything inside of those hex 80 bytes, which does encompass all of chunk 3. Now, the reason that this is a useful thing to create is, as you said, I can read chunk 3, but I can also overwrite the size of chunk 3. I could overwrite the next pointer of chunk 3. I could leave the key. I could write a whole bunch of A's until I get to the next pointer and then print out chunk 2, and it would give me the next pointer from chunk 3, right? All of a sudden, I have a whole lot more capabilities. Once you have created an overlapping chunk in the heap, you've pretty much solved every problem you could possibly have when it comes to the heap. But the core nugget of how you get here is understanding where the allocations, where these chunks are located relative to each other. I'm going to quickly modify our code here. So we will have 3 chunks. Hopefully I don't do her wrong. Okay, what is my read bytes 2 pointer? That is 5. What does it want? Slot number. Let's say 0. Okay, so P send line 5 0. Bam. 5 0. I think it wants to know how many bytes. Say 8. Cool. How many bytes do I want to send into this thing? It's a chunk of size 20 is what I'm allocating. Okay, someone says 21. I don't know, I'm going to put 28. I don't know. Is there a way we can know? I don't wanna, but you know what the answer is. How do I make sense and look at these chunks? I just chose 28 for no reason. It felt like a good number. How can we do science and math? You know,
Didn't make a tool.
right? There is no tool, right? We do not have the technology to look at memory and reason about distances. Right? You see how this is all a meme. Right? We okay, take a look here. We'll attach to 2129. What do I want to do? I can type heap bins. Heap bins shows me as a refresher, heap bins. Oh, don't touch the iPad. Do this. Boop. Where'd my cool little heap bins gives me this visualization of what are my bin size, what's my head pointer, what is the next pointer, right? I haven't done anything with that. So heap bins is kind of useless, right? It just says, yeah, there's a T cache and there's nothing in it. What other commands have we seen? All right, there's heap visual or heap visualize heap for Jeff. This gives me a nice color-coded printout of these chunks. Now, I actually don't know where these pointers are, but we can see this right here. There's also, what is it, heap chunk, which shows me, what did we put around there? But it gives me the sizes of the chunks and as well as if they're in use. Is it showing it? Yeah, okay. It's just color coding greatness. So this tells me the address of the chunks and then the size of the chunks. I have to keep my finger here, else we can't see it. But we see that there is a chunk at, for instance, 6C0. The next chunk begins at 6E0. Then we have C70, right? These are all, what is that, hex 20 apart. And we're claiming that the size value is, this is my first chunk that I'm trying to read into. Is there any way I could like dump out the memory of this without using fancy heap tools, just using core GDB? If I know an address, can I look at bytes? We also can't do that, right? This is why you guys are the future, all right? You'll invent these tools that'll do things like examine 8 giant hex at some address, right? I believe that in the future, such individuals may exist. And so this is the beginning of that allocation. If I were to read in A's, I would get them right here. That'd be my first 8 A's. This would be my next 8 A's. This would be my 24 A's. And then I get this right here. What is that?
That's the size.
That's the size. That's the size of the next chunk, right? Oh, right, we've done it. So 20, was it 8 times 3? 24 A's followed by a big number would corrupt the size of the next one. I don't know where this 28 number came from. It came from me, but it was also wrong. So we can use tools to improve this. I'm going to malloc. I'm going to do a slight overread into this allocation. I want to send line A times 24 plus a byte value that is, let's say hex 81, which is what I was using there. And then because I'm running out of time.
Wait, it's not a 24, it's a 25.
Thank you. I'm going to free slot 1. And then we'll just leave it right there. And what I want to see is where attach 2279. Now if I heap bins, I have 1 chunk in the T cache. That makes sense, right? I freed 1 chunk. What bin size is it in?
Hex 8.
Hex 80. What bin size is this actual allocation? When I malloced it originally, it was hex 20. And so now I could malloc something that targets this bin size here, right? I'd have to do some math, figure out what hex 80 is in decimal and pass it in. I'd want to pass in something that's a little bit smaller than that, because this is, I think, one of the traps of GDB. When it shows you the size, you have to sanity check. Is it telling you the size of the allocation or the size of the chunk? The allocation is the like agreed upon user writable region. The chunk includes a little bit of extra, which is the metadata, right? Because we have to have that size value as well. And so I would say if whatever hex 78 is, if we were to malloc that, we could get back the same chunk that was in reality something of size 20, but the heap's not going to give it back to me as if it were something of size hex 8. Does that pass the sniff test? We had something like this. This was our drawing and how we were thinking about it. When we performed these actions, we ended up making if I did one more malloc here, we get back a really big chunk that it swallows chunk 3. This is the idea of an overlapping allocation, and it's another way that we can corrupt kind of the metadata that's used by the heap to create interesting scenarios that can be advantageous to an attacker. Questions, comments, concerns? I'm like 2 minutes over. Somebody asked about white space armoring. Like, white space armoring just means like stuff stops at white space. So just like don't use white space, bro. Like that is really what it boils down to. I did see the question. It's a great question. I agree. That's really what it boils down to. If you can't use white space, then don't use white space characters. Like, I know that seems 5-head, but it really isn't. I'll give it a moment for the Twitch delay. Do you guys have anything else? Cool. This should get you plugged along up until the safe linking stuff. If you brick wall at the safe linking stuff, don't worry, it's a common problem. Safe linking is a protection mechanism that we have had disabled for an old version of libc that everything for the first like 16 challenges or so, 15 challenges, they use an old libc that doesn't use this. Safe linking does like crazy XORing stuff to change values so that you can't just, oh, I get a use after free, let's print this value, it's a pointer, haha, right? Instead, we start doing tricky mangling stuff to make it difficult for an attacker to reason about values that are stored in the metadata. Next week, Thursday, we'll take a look at that. I'll still have office hours, as long as it's not officially a US excuse or university excused day. With that, I'm out of time. I'll let y'all go. Goodbye, good luck. Get her done.